Welcome to lesson 6.4. Now before we jump into this lesson, it would be very helpful to review some things about imaginary or complex numbers that you learned back in algebra. Let's start right here. Let's review multiplying complex numbers. I have two complex numbers here, 3 plus 2i and 1 plus 2i, and I'm multiplying them together. Essentially, we're just FOILing or distributing. A lot of people call it the rainbow method, whatever you want to call it. We just multiply 3 times 1 to get 3, 3 times 2i to get 6i, 2i times 1 to get 2i, and 2i times 2i to get 4i squared. Now, hopefully you remember that I squared is the same thing as -1, so my 6i and 2i become 8i. Turn the I squared to a -1. 4 times -1 is -4, so 3 minus 4 gives me -1 plus 8i. And that's how we would multiply complex numbers together. Now here's what I want you to notice this time. Here I have these two complex numbers. I've taken them and I've graphed them. So here's 3 plus 2i graphed on our complex plane, 1 plus 2i graphed on our complex plane, and then our answer, -1 plus 8i graphed on our complex plane. It might be a little difficult to see, but you might notice that if I take my blue and my green thetas, these two angles, so I take this blue angle and I take this green angle, and I add those two angles together, I'm going to end up with my purple angle. You could also notice that with the r's. If you take the blue r and the green r and you multiply them together, you're going to get this purple r. So this is showing us that there is some relationship between these complex numbers when they're written in polar form, which is what we talked about last lesson. So, polar form multiplication. It looks like, whoa, that was a crazy not straight line. We are going to multiply the radiuses and add the thetas. And that would give us the exact same answer as if we had just FOILed them, multiplied them in the first place. So we're seeing that we could either multiply them this way, like we learned in algebra, or we could turn them into polar form, multiply the r's, add the thetas, and get the exact same answer. Now, as of right now, you would probably stick with this way. This way is much shorter than turning these into their polar form, multiplying the r's, adding the thetas, and then changing it back to this form. That takes quite a while. However, that's because this is a fairly simple problem. The problems are about to get more complex. Let's say we dive into dividing. This one may be pulling a little bit farther back. Dividing complex numbers. If you have two complex numbers, this time I have 1 plus 3i and 3 plus I. If you want to divide them, you have to multiply by the conjugate of the denominator. So instead of 3 plus I turn it into 3 minus I, and I multiply by that conjugate on top and bottom. So I do my little rainbow method on the top and bottom to get these, do my simplifying just like I did last time, and I end up with something like this. I divide both pieces of the numerator by the denominator to get 6/10 plus 8/10 I, and simplify it to get 3/5 plus 4/5 I. That is quite a bit more work than multiplying. Kind of more obnoxious. More algebra going on here than what we did in the last problem. However, once again, you'll notice there's a pattern in the polar form. If I take this green theta and I compare it to the blue theta, you may notice that if I take the green theta and I subtract the blue theta, that's how I get my purple theta, my answer. So if you're dividing, instead of adding the thetas, we're subtracting them. Also with the r's, if you take your green R and your blue R, you may notice that we divide the two R's to get our purple R. So just like we had a rule for polar form multiplication, we also have a rule for polar form division. We divide the R's and subtract the thetas. And this is where we start to see that maybe doing this in polar form is easier than remembering this process. They're probably about the same amount of work either way, depends on the kind of numbers you're working with, but it might be easier to change these into polar form, divide the R's, subtract the thetas, and then turn it back into rectangular form to get the same exact answer. So you could do this process or this process, same answer either way. Now, let's make it even more complicated. Let's say instead of multiplying or dividing, I gave you something like this, an exponent. And I wanted you to multiply 3 plus 2i 5 times. This is where the problem starts to get pretty gross if you try to do it algebraically. If you just like blunt force multiplied all of those, that would take you forever. However, there is a polar form rule for exponents. It is called de Moivre's theorem. Mr. de Moivre is who discovered it. If you put this into polar form, all you would have to do is raise the radius to your exponent power and multiply your theta by that exponent power. You could do this, change it back into rectangular form, and you would get the answer to this, which this is now going to start to be way faster than trying to multiply that out all those amounts of times. And even gets grosser. What if I asked you to take the fourth root of a complex number? That we actually cannot do algebraically. There's not really a way. However, there is a polar form rule for being able to do this. So instead, we would change 1 plus 2i into its polar form, r cis theta, and do whatever rule, we'll talk about it in the next video, what it is. And that's how we do this instead. So, in summary, we can multiply complex numbers, we can divide complex numbers, we can raise complex numbers to an exponent, and we can raise them to a root. We could do that algebraically for these three. However, what we're going to be learning in this lesson 6.4 is the rules to do these in polar form instead. For some of these operations like multiplying, either rule is probably the same amount of work. Whether you do polar form or multiplying, you'll get the same answer either way. But once you start to get into more and more complicated problems, you'll find that the polar form is actually faster than doing all the algebraic work. So, in the next video, we'll actually start to look at a couple different problems where we practice these polar form rules and talk about how they work.